Hi class, we are on to the next section, chapter 7.2. We're going to talk about span and linear independence. So a lot of what we're going to see today are things that we've covered before. We're going to repeat a couple of definitions, which is always a good thing, especially when it comes to span and linear independence, because these are generally ideas and concepts that are hard for students to grasp. Not only are we going to repeat things, but we're going to look at this again in a different light, okay? So normally we've been looking at span and linear independence under the guise of vectors, okay? But in the last video, we expanded what we think of as a space, right? So our vector spaces are not only just the traditional vectors. They can also be functions, they can be matrices, they can be sets of numbers, things like that. So now we're going to look at span and linear independence through the lens of any vector space. Okay, so we're going to be playing around with objects that you're familiar with, but we have not been using in this class yet. Okay, so let's go over the definition of span one more time. So suppose we have a set that we call V that is full of objects, okay, that are non-empty, okay, and let's say we have a finite number of these. So we have M of these, and this is a set that is contained inside of a vector space. So remember, a vector space has 10 axioms that it satisfies. It's a collection of items that satisfy 10 axioms. 5 of those axioms are related to addition, the other 5 to scalar multiplication. When those axioms are satisfied, we call this a vector space, right? So these are vectors that are inside of my vector space. Then we say that the span of this set, so all the objects that this set can generate by adding them together in linear combinations, is denoted as the span of V. So again, notice that this fancy V here is different from this V. This is just a set of objects inside of this vector space, right? So this is the span of this set of objects, is the set of all linear combinations of the form some constant multiple times the first vector plus another constant multiple times the second vector, so forth and so forth, across all the vectors, right? So all the combinations of these things creating new vectors, by the way, right? We're adding these things together, it will create a new vector. So all the vectors that I can create by adding these together in this way, right, with different constant values here, is the span, right? So here each CI is a scalar value. If V contains infinitely many vectors, if there's an infinite number of vectors here, not finite, then the span of V is a set of all linear combinations of finite sets of this set of vectors. Okay, so let's do another theorem. If V is a non-empty subset of vectors in a vector space V, so really just kind of what we had here, right? So I have a subset of vectors from my vector space, then the span of that set of vectors is a subspace of V. So this is nice now, because before, to prove a subspace, we had to go through the 3 axioms, right? It was that the 0 vector is inside of that subspace, that it's closed under addition, and that it is closed under scalar multiplication, right? So here we're saying as long as this set of vectors has something in it, right, then the span of these vectors is a subspace. So not all the vectors, so if there's only 3 vectors here, those 3 don't make a subspace, but the span of those 3 vectors would make a subspace, right? Linear independence. So suppose that V is this set of vectors again, okay, and there's a finite set of these vectors, so M of them, right? Then V is linearly independent if the following equation, so basically this equation equaling 0, right, has only the trivial solution. So again, this is our previous definition of linear independence, This is our previous definition of span. The difference here is that we are looking at it in terms of a vector space, right? How does this set relate to a vector space? Before we're saying that these things were in Rn, right? Now we know that a vector space is not just Rn, the n Euclidean space. It can be several different types of spaces. So these are several different types of objects now at this point, right? So if this is the only way to make R zero vector, again, this is the particular zero vector for my vector space. If this is the only way to get that zero vector, it should have only this trivial solution where all of these things are zero. Okay. Otherwise, it's linearly dependent. If there's a solution to this that is not the trivial solution, then it's a linearly dependent set. Okay. If our set here is infinite, there's an infinite number of vectors, then our set is linearly independent if every finite subset is linearly independent. So what does that mean? It means that if I took just one, that one vector would be linearly independent. If I took just two, those two vectors have to be linearly independent. If I just took three, those three vectors would have to be linearly independent, and so forth and so forth and so forth, because there is an infinite number of vectors. So any finite subset I take of that infinite set would have to be linearly independent. If that's true, then this set of infinite vectors is linearly independent. All right. All right. So another theorem, a set V of vectors in a vector space V is linearly dependent if and only if one of the vectors in that set is in the span of the other vectors in that set. So again, this is a theorem that you guys are familiar with as well, right? So we really haven't gone over anything new yet except for this theorem here, where we're saying that the span of a subset of a vector space is a subspace. This is the only new thing here. Everything else we covered way back in 2.3 or 2.2. I think both of those actually, right? So the next theorem is that suppose we have a set V that is a subset of vectors in a vector space, then 1, or A, is that this set of vectors is linearly dependent if and only if for every vector in my vector space, not in my set, but for every vector in my vector space, I can write that vector as a linear combination of these vectors. So again, just think of basis, right? As when you have a basis, you can create a new vector by writing it as a linear combination of those basis vectors. It's really the same thing. Any vector in my vector space should be able to be written as a linear combination of my subset here. If that's true, then this set is linearly independent. Okay, and it should have at most one solution. So what does this mean? It has a unique representation. There's only one way to represent this vector, any vector in V, as a linear combination of this set of vectors. Okay. We say that the set here spans my vector space if and only if for every vector I have in my space, okay, this vector representation, right, this linear combination of these vectors has at least one solution. Okay, so meaning that I have only one solution, or I can have multiples. So again, if this is a unique representation for both cases here, then we can call this a basis. However, if there's more than one representation here, it spans, but it would not be linearly independent. Okay. Now, if this representation has only one solution, but it doesn't work out here, then it would not be a spanning set, right? That here you would have not enough vectors, basically, right? So let's do an example. Okay. So again, we've seen all of this stuff before. We're just using a new idea of what we represent as a vector. Okay. So here we want to determine if the vector v, which is represented by this polynomial, is in the subspace of P3, which it is, right? Given by span x cubed plus x minus 2, x squared plus 2x plus 1, x cubed minus x squared plus x, right? So we want to know if this is inside of the subspace of P3 that is generated by the span of these three vectors. So remember, our definition of vector is different now, right? So is this vector in the span of these three vectors? Okay, so what we would need is that I have some constant multiple of the first vector plus some constant multiple of the second vector plus some constant multiple of the third vector to equal my vector. That's what it means to be in the span. Okay, so again, it's the same definition we had of span before. We are just using different objects now, right? So, can I write V as a linear combination of these three vectors? Okay, that's my question, right? So that's what I want to do. I want to set up this equation. I want to start moving some stuff around to try to turn this into something I'm familiar with, right? A matrix, so that I can do all of my fancy matrix work, okay? So, let's take, again, constant multiple of the first, constant multiple of the second, constant multiple of the last. So some value, some scalar times my first vector in the span, plus some scalar times the second vector in my span, plus some scalar times the third vector in my span, and that needs to equal the vector I'm interested in, right? So C1 times V1 plus C2 times V2 plus C3 times V3 equals V, right? So what does this give? Well, I can just relate. If I were to multiply this C1 across everything, right, which I don't really need to do, but I could have, you notice for that x3, okay, for the x cubed terms, there's only C1. There's no x cubed here. There's this one, okay. For the x squared terms, I have C2, just C3, and this C2, right? C2 here, and this C3. For my x terms, I have C1 times x, C2 times 2x, and C3 times x. So for the next one, I'm going to do the constants. So that's negative 2C1, a C2. There's no C3 term here for that. Okay, so negative 2C1 and a positive C2, no C3. So when I add those together, okay, all I did was rearrange things, right? I rearranged, I factored basically all the x cubed terms and the x squared terms and the x terms and the constant terms, and that should still equal x squared plus 2x minus 1. So now that allows me to take my coefficients and equate them to what I have on the right hand side. So C1 plus C3 will equal 0 because these x cubed terms I have here, there's no x cubed terms on the other side. So that should be my first one. This should equal 0. This should equal 1. Okay. These are the coefficients for all of my x's. So when I add those together, it should add to 2. And these should add to negative 1. So that gives me this matrix. Okay. So again, these spaces are just because I'm trying to organize it so I can easily throw it into a matrix, right? But C1 plus C3, C1, C3 equals nothing. There's no cube terms on the other side, right? C2 minus C3 is 1. C1, 2C2, C3 equals 2. And then this equals negative 1. Okay, so we got everything where it needs to go. Very easy for me to then throw this into an augmented matrix. Okay, and I want to point something out to you because this is actually the long way, right? You guys do this a couple times, you'll be like, oh, there's a pattern to this. So notice here, okay, look at my first vector. 1, a 0, a 1, a negative 2. There's no x squared term. 1, 0, 1, negative 2. I can write these as column vectors. If you know that, you can go from here to here right away. You cannot write these as row vectors and try to get away with the same thing. It's not going to work, okay? So again, the safest way is to rearrange everything, make your equations, and come here. But when you're used to this, you can be confident that these are just now your column vectors, right? 0, 1, 2, 1, 0, 1, 2, 1. There's no x cubed term, right? Same thing here. For C3, there's a 1, a -1, a 1, and a 0. Okay, and then of course this is my equality vector, my right hand side, 0 x cubed terms, an x squared, 1, a 2, a -1, right? So as we've stated before, you guys already know how to do all your row operations, so you don't have to show me that work. Just throw this in your calculator, RREF form, right? And you will get this out. Okay, so as long as you know how to interpret this matrix, we're fine. Well, it says that nothing is equal to 1. That's an inconsistency. That means that this isn't going to work out. Okay, if it's not going to work out, that means what? That this is not in the span of your set of vectors. This did not work out. Okay. So therefore V is not in the span of this set of vectors. Okay. So again, we're taking things that we're not used to and we're just trying to transform them into something we are used to. Right? Let's do another example. So let's determine if sine squared of x, cosine squared of x, and 1, this is a set of vectors, is linearly independent in the set of functions from the interval 0 to pi that are continuous and differentiable. Okay, so smooth functions. So what we need then is we need C1 times our first vector plus a C2 times our second vector plus a constant times our third vector equaling 0, because 0 is the 0 vector for functions. Okay, you add 0 to any function, you'll get that exact function out. So 0 is our 0 vector in the function world and the polynomial world as well, right? So we can actually just move stuff around here. Okay, since we have this identity, sine squared plus cosine squared equals 1, we really have this is 1, right? If we let C1 and C2 be 1, then we have 1 plus some C3 equals 0. So then that means we can just have C3 be -1, right? We just move this identity around. It's very easy to see that this is a solution. And the solution that we do have is not the trivial solution, okay? And since this is not the trivial solution, that means that we are linearly dependent in this vector space. Because, so again, 1 is in the span of these two vectors. All right, I can write a linear combination of these two vectors to get out 1. In fact, this plus that is 1. The linear combination is just the constant coefficients of 1. So that means that it is not linearly independent. It's in the span of the other two vectors in the set, right? It's in the span of other vectors in the set, so it's not linearly independent. It's a linearly dependent set. Now, this was a neat example because there is it's an identity, right? It's something you guys are used to. But what if it was something that you weren't used to, right? Let's say it's just some off-brand function that you're not used to, and you can't tell just by looking at it that one of these is in the span of the other. Okay, so we have something else that's good for that. It's used a lot in differential equations. So if you're taking a Diff-EQ course right now, or have taken a Diff-EQ course, you've either ran across this or you will be running across this soon, right? So it's what's called the Wronskian. So the Wronskian is named after a person, the person who developed it. And so what it is generally notized by W of X, where the input here is the functions that you are interested in. Okay, So if I want to find the Wronskian of these functions, I would generally write it as W sine squared, comma, cosine squared, comma, 1. That's how we would generally write the Wronskian. It's linear algebra, so it's not diffie-Q, so we have a little bit more flexibility in that, right? But the way that it works is you write your functions, across the first row, okay? Then you start to differentiate it. So this next row would be all the first derivatives of the functions above it, okay? Then your next row would be the second derivatives, and so forth until you get to the n minus 1th derivative. So what that does is you now have n functions across and n entries down. So this will turn into an n by n matrix. But again, notice it's not a matrix. Straight bars denote that you are taking a determinant. Okay? If this determinant that you take here is not 0, then your functions are linearly independent. So it's very similar to how I said earlier in the determinant section that I like to find linear independence to let me know whether something is invertible or a basis or etc., etc. I just write the column vectors and then I find the determinant. It's very, very similar to that, except that you're not writing the coefficients down, you're not doing any of that. You're using the actual functions and you're taking their derivatives, and then you're finding the determinant. So let's go ahead and do an example. Use our previous example. I think that'll be the easiest thing for us to do since we've already know what it is. So let's take the Wronskian of sine squared x, cosine squared of x, and 1. So when I write this into my determinant matrix, okay, I write the functions in the first row. I find their derivatives. Okay, I'm not going to go over these with you. You should know how to do this. This is a chain rule, right? You take the 2 down, you multiply it times your function, and then you multiply that times the derivative of the inside function, which is the sine. So sine goes to cosine. S stands for sine stays the same, right? So you don't change signs. Here, same thing, but you have cosine. So C is for changes sign. So you have the cosine times the sine, and it changes sign, so it turns into a negative, right? That's how I remember it, at least. Our next line is going to be the second derivative, and that's where we would stop, because then I'll have 3 rows, and I'll have 3 columns here, right? So I know I'm going this way for columns, but that's because there's 1, 2, 3 columns, right, along the 3 rows. So my second derivative looks as such, okay? And so the easiest way to find this determinant, well, I mean, I guess doing the 3 by 3 multiplication is not that bad. But notice here, I got a 1 and all zeros. So if I go down this column, my cofactor expansion is positive, negative, positive, right? So I have just a negative 1, so it doesn't do anything. I delete this row, delete this column, and I'm just finding the determinant of this 2 by 2 matrix. Super easy here, okay? So we take the first term times this first term. That gives me a negative 8 sine cosine cubed, okay? Then I multiply this times the 2. I'm really just distributing this single term across these 2 terms. I know it's functions, and we're not used to them in this class so far, but it's really easy mathematics, right? So we're just going to double everything here. So 4 sine cosine. And then I'm going to subtract from that the same thing here, right? So I'm going to multiply this times here. So subtract a negative 8 sine cosine cubed, right? So minus this. And I'll also be subtracting this positive 4 sine x cosine, all right? And if you notice, what I have here and what I'm subtracting is identical. So I get out 0. Super easy, super fast. Super easy to understand what the results mean, right? It means, since this is 0, that this set of vectors is linearly dependent in this vector space. Okay, and that's it. Hope you enjoyed this short video.